Unfortunately, the first half of the lecture did not record yesterday due to a failure in the Sony flip recorder. Yes, that's a Sony flip recorder. So what I'm going to do is I'm going to just quickly review what we did in the first 20 minutes. So we were talking about optimization. And so we've seen how to optimize functions of one variable. And so what we're going to do is we're going to quickly review how to optimize functions of one variable. What are the techniques, what are the methods, what are the issues. And then we'll talk about then the generalizations to several variables, and we'll see the difference in behavior in going from one dimension to two dimension. And a lot of this will resurface when we get to linear programming. So the goal is we have a function f of x that's nice. So nice is one of the most frequently used words in mathematics, and depending on what you're looking at and depending on what your mathematical prerequisites and background are, the word nice means different things. So since we're reviewing what we've done in calculus, for us nice will mean f is continuous, differentiable, maybe continuously differentiable. Actually, as a nice exercise, if your function is differentiable, it's automatically continuous, but let's just be simple and just state this to begin with. Alright, so the question is, how do we maximize a function? And so whenever I ask this question to my students, they always say the following. So procedure, compute f prime of x, find all x such that f prime of x equals 0. These are called the critical points. And check them. And so this is really good, and this will get a good chunk of what's going on, but unfortunately it doesn't get everything. And so the common example I use is, imagine I am running, and we want to find where is my speed largest. So the goal here is we're going to have a function f from some interval a, b to r taking on real values. And so maybe I'll start over here in the room, and I will travel, and I'll be at different speeds all the way to here, and the question is, where am I fastest? And so if we look at my flight path, I guess I'll do it backwards, it's a little bit better for the camera. So the question is, of course, where was my speed greatest? There was no place where my first derivative vanished. My speed was actually greatest when I crashed into the blackboard. And so when we're doing arguments like this, it's extremely important to remember one other thing. Alright, so restore this. Also check endpoints. So this is one of the most forgotten things in optimization in Calc 1, is people forget to check the endpoints all the time. And so we'll talk in a few minutes about why the critical points give us candidates, and we'll talk about the need of checking endpoints. Now fortunately, the endpoints are very easy to check. There aren't that many. If I give you an interval a, b, there's at most two, a and b. Maybe b is infinity or a is minus infinity, in which case we only have one. Or maybe they're both infinities, in which case we have 0. So the number of endpoints in one variable is sufficiently small that it's really not that big of a hassle. So the question is, why is checking the critical points, why is that one of the steps? Why are these candidates? And so let's look back to the definition of the derivative. F prime of x is the limit, as h tends to 0, of f of x plus h minus f of x over h. And let's look and see what happens. I'm just going to check and make sure it's recording. So, yep, it seems to be recording. So I'm going to just look and talk a little bit about why the critical points matter. Let's assume f prime of x is greater than 0, and let's see what implications that has for a function f. And of course we could do a similar argument if f prime was less than 0. Alright, so we're going to assume this. So there's two possibilities for h. Case 1, h is greater than 0. So here's x plus h, and we're heading down to x from above. Well, if we look at our expression, if this whole expression is positive, because we're assuming f prime is positive, and h is positive, then if h is sufficiently small, the numerator must be positive. So this means h small, f of x plus h is greater than f of x. So my function has to look something like this. it's got to be larger than x as I go to the right. So, okay, what about case 2? H is less than 0. So here's x plus h, and we're now rising up to x. Well, if h is negative, and this expression is positive, the only way that can happen is if eventually, for small h, the numerator has to be negative. So this means, in this case, when h is small, f of x plus h is less than f of x. So we can also say that over here, as we go to the right, our function increases. Over here, as we go to the left, our function decreases. So it's going to look maybe something like this. So what this tells us is x cannot be a maximum or a minimum if f prime of x vanishes. And the reason is it can't be a maximum because I just go a little bit more to the right and my function got larger. It can't be a minimum. I go a little bit back. Sorry, I said left before. Sorry. If I go a little bit to the right, I get larger. If I go a little bit to the left, I get smaller. If instead of looking at f prime of x being greater than 0, we look at f prime of x less than 0, all we do is we flip like this, and now if we go this way, we're increasing, and we go this way, we're decreasing. So if we're going to have a maximum or minimum, the only thing left is f prime of x has to be 0. So max min, it's necessary for f prime of x equals 0 to be a max or min at x. Now there's a big difference between the word necessary versus the word sufficient. So necessary means it must happen. But just because it happens doesn't mean that our conclusion holds. Sufficient means that if this sufficient condition happens, then we would be assured of having a maximum or minimum. So let's talk a little bit more about the difference. So here's the standard example that I think every calc professor is required to give. Let's say f of x is x cubed. Well, f prime of x is just 3x squared. So what we notice is the derivative is positive everywhere except the origin. And so if we plot our function, it's going to look something like this. And so we see that even though the derivative is 0 here, this is neither a maximum nor a minimum. So while it's necessary for the first derivative to vanish, it's not sufficient. And this case shows why. And so this leads to the search for sufficient conditions for a critical point to be a maximum or minimum. And so you might see things like the second derivative test or the sign of the first derivative on both sides. So second derivative test and first derivative test. The goal here is for sufficient conditions. Now something I've been saying in all these arguments is looking for when the critical point is a maximum or minimum. And you were saying that we can't have a maximum or minimum without a critical point. Well, we actually forgot something. It was the example we did earlier. We have to remember the endpoints. And the reason is if we go back to argument, f prime of x was the limit as h goes to 0 of f of x plus h minus f of x over h. And we had our little plot here, and if h was positive, we were coming down. Well, implicit in this argument is the fact that we can take an h greater than 0, that we can get past that x is not a boundary point. And so when we're looking at the speed issue, when I started here, and then for each location I gave you my speed up until here, my speed was accelerating. If I could have gone further in time, I would have gone even faster, but the problem is I hit the blackboard and had to stop. So the first condition, the first derivative being 0, is a great condition to help you find candidates for the maximum and minima. But unfortunately, it's not the only thing you have to look at. You have to check the boundary points as well, because the whole argument of the first derivative rests on the assumption that we can actually take the derivative. We can study the function in some interval, that we can go a little bit above and below. And so here, if we're at an endpoint, we may not be able to do either the above or the below. Now, whenever you have candidates, it's worth getting a sense of how many are there. So, how many candidates? Well, fortunately, the endpoints is manageable. Endpoints at most 2. Critical points. Well, this is a little tricky. This could actually be a lot more. For example, let's say f prime of x is x squared sine of 1 over x. This function has infinitely many zeros in a small interval about the origin. And so unfortunately, there could be infinitely many points to check. Now, most of the time we're not going to have terrible pathological functions like this. But it's important to be aware of the existence of such issues like this. And so what we do from all of this is we get a set of candidate points to check for maximum and minimum. We get a set of candidates for optimal values. And then we just evaluate the function of these and see which one is largest. Okay, so this is one dimension. So the next question is, what would happen if we go to 2 dimensions? So now, maybe we want to find the maximum or minimum of some function f of x subject to some condition, maybe g of xy less than or equal to c. And you can begin to see that this is going to be ideally suited for what we want to do in linear programming. We're going to have a set of conditions, a set of constraints, and we're going to have some function we want to optimize. So for example, the standard is g of xy is x squared plus y squared. So g of xy less than or equal to c is a circle of radius square root of c. And you can probably guess what the standard value we would take for c is. Alright, so we want to find where is f largest or smallest subject to this. We want to find what are the candidate points. Alright, well, we have 2 regions. We have the inside and we have the boundary. And so on the inside, it's actually very similar to what we did before. So inside, the candidates are from the derivative of f equals the gradient of f equals grad of f. Anytime you have something that can be written in this many ways, it's important. Equals partial f partial x, partial f partial y equals 0, 0. And the way to look at this is, going back to what we did in one dimension. Always go back to what you did in a lower dimension and try to extrapolate, try to see what the key features. So here, if my first derivative was not 0 with respect to x, well, I could then move in a direction and I would have a maximum. Similarly with y. So I need something like this. A better way of looking at this to really reduce this to something from one variable is directional derivatives. So what we can do now is imagine we take some direction. And what I can do is I can then write my point xy as my starting point x0, y0 plus t times a vector in that direction. And this will give me a line. And then I can now form a new function. I'll call it script f of t, which is going to be f of x of t, y of t is going to be f of x0 plus tv1, y0 plus tv2. So even though it looks like this is a function of 2 variables, this new function is a function of 1 variable. And to find its optimal values, to find its maximum and minima, to find the candidates, all we have to do is go back to 1 variable calculus, which is find where the derivative is 0. That turns out in multivariable calculus to be equivalent to where the directional derivative vanishes. So these are all different ways to see that the inside candidates come from where the directional derivatives is 0. The problem now is, what do we do on the boundary? And so the boundary is the more interesting case. And so this is where we get the method of Lagrange multipliers. And the condition, or conditions actually, I should probably write conditions, is the following. the gradient of f is some multiple of the gradient of g, and g of xy equals c. So the important thing to remember is we really need to remember to include the g of xy equals c. And the reason is if we unwind this, we get df dx equals lambda dg dx. df dy is lambda dg dy. This is two equations, but in three unknowns, x, y, and lambda. So if we want a chance to really solve this, we need a third equation. Our third equation is this constraint. G of xy equals c. And now we have three equations and three unknowns. One thing that's important to emphasize is that even though lambda often has some physical or mathematical economic significance in the problem at hand, if we're trying to find the candidate point xy, we don't care about the value of lambda, except so much as it helps us find the values of x and y. And so one way you often solve formula like this is you take the ratio of these two equations, and that cancels the lambda, being very careful not to divide by 0. So why is this the case? Well, it turns out the gradient of g, if this over here, the boundary, is the curve g of xy equals c, the gradient of g points in the direction of the normal to the surface. So imagine now we have the gradient of f at some point, and the gradient of f is not parallel to the gradient of g. That's what this equation means. This vector with two components is in the same direction as this vector with two components. Well, I could then write f, the gradient of f, as some part in the parallel direction, the same direction as gradient of g, and in some amount perpendicular to that. And what this is telling me then is my function f would actually be increasing as I go in this direction and decreasing as I go in that direction. And so I can't have a maximum or minimum unless the gradient of f and the gradient of g align. So of course this is assuming these gradients always exist, so that our functions are sufficiently nice, the region we're trying to optimize over is sufficiently nice, but these conditions are typically met in many interesting problems. And so we get these wonderful sets of conditions that for the interior maxima minima, the candidates are where the gradient vanishes, and for the boundary, the candidates are where the two gradients are parallel. And again, going back to one dimension, it's worth thinking about how many solutions can we have to this. We have three equations and three unknowns. Should this give us only finitely many solutions? Do we expect to have infinitely many? How many are there to check? In a lot of problems of interest, fortunately, there are only finitely many to check. But it is a real issue. There's far more points on the boundary here than there are on the boundary in one variable. In one variable, the boundary was just the endpoints. So either 0, 1, or 2 endpoints. That's not that bad to check by brute force. Here, there are infinitely many points on the boundary. If we don't develop a new theory, a new method, we have too many points to just check by brute force. And this is why something like Lagrange multipliers is needed. An interesting question is, could you develop an analog of Lagrange multipliers for functions of one variable? It's a nice exercise to try to do that, but the question is, how intense would it be to apply a method like that versus what would the savings be? Because again, in one variable you only have two boundary points to check. Now, just a couple of general remarks, because unfortunately I don't remember exactly what I mentioned to my students in what order. I only remember approximately. I talked a little bit about the need for physical solutions, or physically reasonable solutions. And so often when we're doing optimization problems, some of the solutions we have to throw out. So there's the Farmer Brown problems. So he has cows, and he loves rectangles. And he will only consider pens that are rectangular. And so the question is, what pen can he have, and this is a really bad cow, that will maximize the area his cow has to graze if it has to be a rectangle? Sometimes you have his brother, Farmer Bob, who is fortunate enough to be building his rectangular pen either on the boundary of a river or a mountain range, so my art is bad enough so there can be either, and now he only has three sides. And often when you're trying to solve optimization problems like this, you'll end up getting a quadratic where one of the solutions will be positive, one of the solutions will be negative. And from physical grounds, we'll throw away the negative solution. All right, so last thoughts about optimization. So when we're doing all of this, it's worth remembering what is the difference between one dimension and two dimension. And if you've seen Stokes' theorem, this is a beautiful result that the integral of d omega over some c is equal to the integral over the boundary of c of omega. So here omega is a differential form. This is essentially the fundamental theorem of calculus. If I take the integral over an interval of some function f of x, this is telling me this is the integral over the boundary of the region, and the boundary has to be appropriately defined of the antiderivative. And so here, that's going to just be f of b minus f of a. So the fundamental theorem of calculus has this wonderful interpretation relating the derivative of a function to a region to the antiderivative over the boundary of the region. Now, imagine you have a closed curve. Well, in one variable, the only closed curve you can have is essentially a point. If I walk forward and then walk backwards, I've retraced my steps, those two cancel. So in one dimension, all closed curves are trivial. And so there, my interval would actually just be a point. And that would lead to f of a minus f of a is 0. And so the integral over my closed curve of df would always be 0. And it's 0 for a trivial reason. I don't have any interesting closed paths to take. But when I get to 2 and higher dimensions, the geometry changes. I can now have a non-trivial closed curve where I end up where I started. But I haven't ever gone back, I haven't ever backtracked. And so again, it's always important to look and see, as you change dimensions, as you go up, as the dimensions increase, what issues does that bring up? Okay, so the rest of the lecture hopefully recorded. In fact, I think it did record, and the lecture continues then with talking about canonical forms and solving the type problem.